Okay, in this talk I will present a joint research project that I started with Olivia Caramello, and the aim of this research project is to study the context and the theory of MV-Algebras from a topos-theoretic point of view. And what does we obtain until now? We start to study categorical equivalences that are already known in the theory, in the context of MV-Algebras. And what we do is what already mentioned Olivia in his course. We started with this categorical equivalence, and another question is this Morita-Equivalence induce a Morita-Equivalence between the theories that are involved? And we asked for, in an affirmative way, for these two categorical equivalences that we study. We study in particular Mundich's equivalence. It is a categorical equivalence between the category of MV-Algebras and the category of lattice ordinal million groups with strong units. That, you know, it's the names of this structure is very long, so I will come for short just L groups with strong units. And the other categorical equivalence that we look at is the null-related equivalence that prove that the equivalence between the category of perfect MV-Algebras and the category of L groups. And what we do once we prove that we can actually lift these two categorical equivalences is to, of course, apply the bridge technique to these equivalences, because, as Olivia said, it is very nice. Once you have these Morita equivalences, you can apply the bridge technique in order to transfer information from one theory to the others, or just obtain new information on the theories. And in a recent work, we actually work in the opposite way. We actually construct new classes of Morita equivalences that among this class, we obtain also as a particular the null-related equivalence. So one of these Morita equivalences that we construct is indeed the lifting of the null-related equivalence. But the results that we obtain in connection to the lifting of Munch's equivalence, applying our bridge technique, is the first one. The first immediate result is that the theory of L groups with strong unit is a theory of preshift type. And we obtain this result very easily because this theory is Morita equivalence to an algebraic theory that is the theory of MV-Algebras. And of course, we consider other invariants, and we obtain also these second results that say that the quotients of these two theories are in bijection. Let me remark the fact that this result cannot be obtained just consider the equivalence at the semantic level, because what does the categorical Mundich's equivalence say? It says just that if we restrict the categorical domain, let me say we have a restriction on the categorical codomain, and we have that these two categories are still equivalent. But here we have more. We say that if we had, for example, some action to the theory of MV-Algebras, you know that there are some action that you can add to the theory of L groups with strong units, and you obtain two quotients of these two theories that are still Morita equivalent. And the most important factor and the non-triviality of this result is that these two theories are not bi-interpretable. Of course, if you have if you have a way to translate from the language of one theory to the other, these results would be very trivial. But in this case, we prove that these two theories are not bi-interpretable. And we can obtain in an indirect way this bijection, because as Olivia said in our course, every sequence can be written in this form. Where these formulas are irreducible. And since we proved that indeed there is a bijection, yes, it's not exactly in this way, but for easier, I just write, yes, here I have to write like, where these are rocks. As is, yes, sure. Okay. And So this, since we proved that there is this characterization for the finitely presentable L groups, and we proved that indeed that every finitely presentable L group with strong unit is indeed finitely presented. We have a way to we have a bijection between the reducible formulas that can implies in a direct way this bijection between the quotients. And also we prove a form of compactness and completeness result for the theory of L groups with strong units, just considering an invariance, just transferring some information that we know for the theory of MV-Algebras. So just consider certain invariants. And these results are very surprising because the theory of L groups with strong unit is an infinitary theory. It means that we need of an infinitary disjunction to express the property to be a strong unit. And so you can imagine that prove that an infinitary theory is complete a priori can be very difficult, but we obtain this result just as an application of the bridge technique. So just transferring some information, we will see.
Precision. When you say completeness, it means that it satisfies a completeness theorem with respect to the set-based model.
Yes, sure. Yes, sure. Yes, you say in your course that every geometric unit is complete with respect to models in any universe. So here we say complete with respect to set. That is not. This is that is not true for every geometric theory, of course. And we proved also a shift-theoretic version of this Mundish's equivalence. Indeed, we proved that if you consider the category of models of these two theories in any topos of shifts on a certain topological space, then you have again a categorical equivalence that is natural with respect to the topological space. But just let me list the results that we obtain applying the bridge techniques to the other equivalence, that is the lifting of the de Nollet equivalence. We obtain again, as an immediate result, that the theory of perfect MV-algebra is of preshift type. And this is true because it is Morita-Equivalence to an algebraic theory that in this case is the theory of L groups. And even in this case, we prove that these two theories are not bi-interpretable. But if we restrict they are not globally bi-interpretable, but we found three partial levels of bi-interpretation by considering as many invariants. So just considering invariants, we obtain a bi-interpretation at the level of irreducible formulas, at the levels of geometric sentences, and at the level of imaginaries. But we will see later how invariance will lead to this result. And we obtain also that every finitely presentable models of the theory of perfect MV-algebra can be is finitely presentable also in the variety that is generated by the perfect MV-algebras. And of course, the converse direction is true because every finitely presentable object in the variety is finitely presented with respect to the theory of perfect MV-algebras, but the other sense is not trivial, and we prove also this result. And finally, we obtain this representation result for finitely generated algebra in the variety generated by perfect MV-algebra by studying. This is the very new technique that we used by studying the classifying topos of the theory of perfect MV-algebra, and more particularly by studying the classifying the Grundig topology associated with the theory of perfect MV-algebra, regarded as a quotient of the theory of the variety generated by this perfect MV-algebra that in the following I will call just Chang's variety for brevity, for sure. But we say that we construct new Morita-Equivalences, and we actually I say in the opposite way, because in this case we prove first that the theories involved with are of preshift type, and we studied the theory of local MV-algebras in an arbitrary variety, and we proved that globally this theory is so if we consider the theory of local MV-algebra in the whole variety of MV-algebras, this theory is not a preshift type. But if we restrict this and we regard the theory of local MV-algebras in any proper subvariety of the variety of MV-Algebras, then these theories are of Presheaf types, and we prove that these theories are Morita-Equivalents to certain theories that extend the theory of L groups. And how we prove that? We prove because we obtain that these two theories are both of Presheaf type. In this case, to obtain the Morita equivalence is sufficient to prove the categorical equivalence of the models, of the categories of models at the level of sets. But this is just a particular case if both theories are of Presheaf types. And again, we obtain that finitely representable models of this theory of local MV-algebra in a proper variety are also finitely presentable with as an object in the variety that we choose. And again, we obtain this representation result for finitely generated algebras in the variety as finite products of local MV-algebras, of course, in the variety. But before going into the details of these results, let me just recall you the definition of the structure that are involved in these equivalences, both Morita or categorical. And so we have the notion of MV-algebras that can be seen as, that is indeed the semantical counterpart of infinite Lukasiewicz logic. And so I would like to say that infinite Lukasiewicz logic is like give a more appropriate description of the reality with respect to classical logic, because in reality you have that everything is not just black or white, so it's just not true or false, but you have a scale of gray that is described very good by this logic, because you can see, for example, that the one models of this, the standard models of this theory is the unit interval 0, 1, where the operation, the plus and the negation are defined in this very easy way. In the following, just for the notation, I indicate with MV, the theory of MV-algebras.
What does it mean, by the way, this acronym MV?
Many-valued.
Okay.
Yes, many-valued. And
Many-valued logic?
Yes, many-valued logic, you have many-valued algebras. It's very, not very, how you say? Yes, yes. And creative, yeah, I want to say. And we have in a particular class of perfect MV-algebras is the class of perfect MV-algebras that are those algebras that are generated by the radical, where for radical you take the standard definition in as intersection of maximal ideals. And we indicate with this symbol the theory of perfect MV-algebras, and we prove that in the particular case of the variety generated by perfect MV-algebra that I call chunks variety, we can describe the radical in this very easy way with just by an equation. And this result, I want to remark on this result because we see that we obtain just a generalization, I can say, of these results later. And on the other side, of course, we have the class of L groups. What is an L group is a group with a partial order structure that is compatible with the group operation. That means that you have translation invariant property. And an element of this group is called a strong unit if it is positive and if it is an infinitary, if it is an Archimedean element. And you can see here in this phrase there is a natural number where the infinitary disjunction appear. And in the following, I will just indicate with L the theory of L groups and LU the theory of L groups with strong unit. So what we obtain, we say that for the first two Morita equivalents, we have the same general patterns, we can say. So we regard the two categorical equivalences as equivalence of categories of models in the universe of sets. And so the natural question is, this equivalence can be regarded can be generalized if we look at the models not just in the universal set but in any universe, so in any Grothendieck topos. And actually we proved that we can generalize these two functors and still we have a categorical equivalence, and this categorical equivalence is natural with respect to the topos because we proved that the construction of these two functors allows also only finite reconjunction and involves only finite limit and algebraic limit, so just geometric construction. And of course, this is just the definition of Morita-equivalence. So we have that the theory of MV-algebra is Morita-equivalence to LU and P is Morita-equivalence to L. But now we finally have these Morita-equivalences, so now we can apply our bridge technique. And so you can see here how we obtain the bijection between quotient. Here we use, this is just an application, if you want, of duality theorem of Olivia, because duality theorem says that you have a bijection between subtoposes of the classifying topos and a quotient of the theory. So since you have that these two theories have the same classifying topos and you regard it as an invariance, the concept to be a subtopos, you have that the quotients of the theory of MV-algebra are in bijection with the quotient of the theory of L groups. As I already remarked, this result is non-trivial because these two theories are not bi-interpretable, and I explained already before how you can obtain these results in an indirect way. So we'll pass to the next results that we obtain by applying bridge technique. This is an application of the bridge technique to the second Morita-equivalence that we obtain, and it's about the three partial level by interpretation that we proved. And you can see that if you consider these three invariants, you obtain the bijection, the interpretation at the level of the two theories. So, for example, if you consider as an invariance to be an irreducible object, the irreducible object in the level of the classifying topos, you have here the irreducible formula for the theory P, and here the irreducible formulas for the theory L, and you obtain the bijection with the interpretation at this level. And again, if you consider, for example, as invariant, the invariance to be the invariance of subterminal object, you take the bijection at the level of geometric sentences and so on. So, as again, we say that this bijection will be trivial if the two theories are bi-interpretable, but in this case it's not.
So there is a topos formulation for imaginaries?
Sorry?
So imaginaries can be characterized in the topos somehow? I don't know how this works.
Well, it's just the pre-topos completion of the coherent syntactic category of the theory. So this you can get from the classifying topos by taking the coherent objects. So what we proved when we say that we don't have bi-interpretability, I mean we don't have coherent bi-interpretability in the sense that we proved that the coherent syntactic categories of the two theories are inequivalent. Mm-hmm. And so it made sense to look for other fragments.
Yes, if we can just consider a subcategory of, can we have by interpretation, can we have equivalence?
Yeah.
So now we can obtain also, as I say, the representation result for this finitely generated algebra in the variety, in chunks variety. And how we obtain this? I say that we obtain this just regarded as at the Grothendieck topology associated with the theory of perfect MV-algebra, regarded as a quotient of the theory of the variety in what we consider in this case. And how we obtain this quotient? We obtain this quotient just by adding this action to the theory of the variety, and this action generate the topology that I can write is just. You take you take an algebra, you take an element in this algebra, and then you consider this quotient, and then you consider finite multi-composition of diagrams of this form. And we prove that if you take an algebra that is finitely generated and you compute a diagram like this by choosing at each step one of the generators. So I can show you the picture here. So we choose at each step one of the generator. You have that these algebras to the end are perfect MV-Algebras. And this proved, for example, that the topology is rigid, and so this is another way for proving that the theory of perfect MV-algebra is of Presheaf type. But how we obtain the representation result? Because at each step, the algebra is a product of the two algebra that we obtain as quotient, because the elements with respect to we consider the quotient are Boolean elements. And thanks to a result that holds in the context of MV-algebra, it is called the push-out, pull-back lemma. This assures us that that A is a product of these two algebras, and of course we can apply this lemma at each step, and we have that A is a product of the algebras at the end. But the question that we want to respond in how is comes from this observation. We know that the class of perfect MV-algebra is just the intersection of the class of local MV-algebra with the variety, with the chunks variety. That is the variety also generated by this algebra that is chunks algebra. That is just an algebras of this form. You have infinite element here and infinite element here. Where you can imagine an algebra like this. And we prove that the theory of perfect MV-algebra is of Presheaf type, and so the natural question is that if there is an axiomatization for the theory of local MV-algebras in an arbitrary subvariety that is still of Presheaf type. And so in the next slide we want to answer to this question. We prove that globally the theory of local MV-algebras is not a Presheaf type. But let me just recall the definition. Local MV-algebras are just non-trivial algebras such that for every element you have that is of finite order, or the negation of the element is of finite order, where the order of the element is just the minimum natural number such that the multiple of the element is equal to 1. And of course this element cannot be exist, and if it doesn't exist, so you say that the order of the element is infinite. And so the question is, okay, globally is not a Presheaf type, but what does it happen if we restrict to a proper subvariety? And in this case, I announced already that the theory is of Presheaf type, but I want to prove you that this is true. So it was proved by Komori that every proper subvariety of MV-algebra is of this form, is generated by a finite list of simple MV-algebras, where simple MV-algebras you can imagine like algebras like this, where this is the Mundich's functor, but can be also regarded as subalgebra of the. Okay. So just subalgebras of the unit interval, where are just of this form. You have 1, 0, 1 m, 2 m. And 1. So this is Sm. While on the other side, you have that this variety can be generated by simple MV-algebras and by Komori chain that are algebras of this form. Okay, you can see the generalization from these algebras and these algebras. Okay, sorry, here Komori chains are of this form. And so on. And so we prove that even if we change the generators of the variety, they have an invariance. So the least common multiple of the ranks of the generators remains the same, and we use this number n to axiomatize the theory of local MV-algebra in the variety. We consider two axiomatizations. The first axiomatization is the following one, that say that every element is in the radical or it is not in the radical. And we prove that the gronitic topology associated to this axiomatization is subcanonical. How we prove that? Because as before, every covering every J1 covering is generated by finite multi-composition of diagrams of this form. But again, these elements are Boolean elements, and so by push-out lemma, we have that this algebra is a product of these two algebras, so we obtain that the topology is subcanonical. Why we need this result? We need this result because it allows us to prove that every Cartesian sequence that is provable in the theory of local MV-algebra in the theory log V is also provable in the theory TV. And this, since it's very easier to work in the theory log V, we use these results to obtain the definability of the radical for the variety in for the algebras in the variety V. But how we obtain this result is just we know that this theory, the theory of the variety, is a theory of preshift type, and so we have the classifying topos of this form, where the classifying topos of the theory of log V is just a subtopos of this, as the whose object is are the shifts with respect to J1, to the topology J1. But the universal model of TV is a model of this form that, thanks to the fact that J1 is subcanonical, is also an object in this topos and can be regarded also as the universal model of this theory. And since the interpretation of Cartesian formulas in these two models in the two different classifying topos is the same, we obtain this result, this Cartesianization, that allow us to prove this definability. We prove everything in the theory log V, and thanks to the Cartesianization, we know that this holds for the theory of TV and in general to the algebras. So just let me go faster. We prove that this result about finite representable models assure us that the condition of the rigidity of the topology associated with the quotient, that in general is just a sufficient condition for the theory to be a preshift type, is also a necessary condition. So we just want to prove that the topology associated to the theory log V is a preshift type. And how we do that? We do that by considering another axiomatization that we obtained considering a description of the radical class of the algebras. And thanks to the fact that these radical classes are compatible with respect to the MV operation, we obtain that the theories of preshift type. In what way? We consider the topology associated to this second axiomatization that is obtained by finite multi-composition of diagrams of this form. And again, for finitely generated algebra, we choose at each step the generators, and we obtain at the end algebras that are generated by element that satisfying one of these formulas. And thanks to the compatibility condition, the algebra generated are again local MV algebras. So we prove that these two axiomatizations are equal, so the Grothendieck topology are the same, and this implies the representation result for finitely generated algebra in the variety V. And finally, how we obtain now the Morita-Equivalence, because there is a theorem proved by Di Nola, Esposito, and Gerla that represent in this way every local MV algebra in the variety. And you see that here we have a group G and a certain K that is the rank of the algebra. I didn't talk very much about rank because I have no time, but you can imagine that the theory of L groups is not enough to be Morita equivalence to the theory of local MV algebras. And so we extend the theory of L groups by adding for any admissible rank, we can say, a predicates, a Zeradi predicates that talks about these ranks. And so we obtain these this theory that I call here Gij, where the axiom are this axiom, and the models of this theory in set can be identified with triples like that, so groups, constant in a group, and K that is it was to regard as the rank of the algebras. And now the definition of two functors are very easy. Let me remark the fact that this theory is of Presheaf type because this is the theoretical group is of Presheaf type. Here we are adding just Cartesian sequence, so this is again of Presheaf type. There is a theorem proved by Olivia that assures that if you have axiom of this form, you still have a theory of Presheaf type. So we say we just have to look about the behavior of the models in set. And how we define the two functions of the categorical equivalence is very easy. For any algebra, we have the representation by Di Nola, Esposito, Gerla. Okay, I finished the time, so okay. But you can see by yourself how the functors works. And the references for the first two Morita-Equivalences are these two papers, and the first one will appear in the forthcoming paper. So thank you for your attention.
Have you questions?
Yes. Excuse this very naive question, but you said there is an equivalence between L groups and so on, and you wrote gamma, but how is it
Define gamma. No, gamma is defined in a very easy way.
Beginning with a group, how do you find an algebra?
Yes, starting with this is the Mundici functors, and it's defined in a very easy way. You take so gamma from LU groups to MV-Algebras. You take a group with a strong unit, and then you just consider. Since these groups are have an order, and so you can consider just the interval at 0u, and in this interval you define the operation, taking as model the operation, the MV operation on the unit interval 0, 1. So the sum is just the truncated sum, and the negation is just the u minus x. So very, very easy definition for the for Mundici functor. Not so simple is the definition of the opposite of the inverse functors. And that's how it was presented is not. It doesn't seem that it is geometric, but we prove in our paper that indeed it can be presented in a geometric way. Also the functor going in the other direction.
The minus is the minus in the group.
Yes, yes. These are operations in the groups, plus and minus, yes.
I think we don't have time.
Oh.